The man who would finally bring order to the elements was a young Russian chemistry professor named Dmitri Mendeleev. He didn't set out to be a savior. He was simply trying to organize the textbook he was writing. But as he grappled with this challenge over one weekend in 1869, Mendeleev would make a discovery for the ages: the periodic table of the elements. Today, it hangs in every chemistry classroom in the world, one of the most familiar images in all of science. But behind the table is a fascinating, untold story. Who was this man, and how did he do it? Mendeleev had recently been named a professor at the University of St. Petersburg, the leading institution in Russia's capital. But getting there had been a long, improbable journey from humble beginnings.
Mendeleev was born in Tobolsk, Siberia, which is basically smack in the middle of Russia if you look at it on a map. It's very much the boonies of Imperial Russia.
His father, the headmaster of the local high school, went blind during the year of Dmitri's birth, leaving Mendeleev's mother to support and raise about a dozen children. Maria Mendeleeva sensed something special in her youngest child. So in 1849, she set out with her 15-year-old son on a 1,500-mile trip by horse-drawn sleigh in search of a school that would accept him. Like most students from the provinces, Dmitri was turned away in Moscow. But in St. Petersburg, he landed a spot in the teacher training school his father had attended. Exhausted by the journey, Maria died a few months later.
She took me out of Siberia and sacrificed what remained of her money, her life, so that I could get an education. From her, I learned that it is through work, not words, that we must seek divine and scientific truth.
Scientific truth was elusive for any young chemistry student in the mid-1800s. There were deep divisions in the field over even the most basic concepts, particularly the atomic weights of the elements. Most chemists believed each element had its own unique kind of atom, and ever since the early 1800s, they'd been working to determine how much an atom of each element weighed.
That's how one distinguished one element from another. So it was crucial to understand what were the correct atomic weights for each of the elements.
Everyone agreed that hydrogen, the lightest element, should be assigned a weight of 1, and that heavier elements should have proportionally higher weights. But that's where the agreement ended.
Did carbon weigh 6 or did it weigh 12? Did it weigh 4? That depended on who you talked to and when you talked to them. By the late 1850s, people were incredibly confused.
This was an unsupportable situation. Something had to be done.
Hoping to sort out the mess, chemists organized their first ever international meeting, held in Karlsruhe, Germany in 1860.
Mendeleev, being a young enterprising student, goes to this meeting and he hears a very important speech by an Italian chemist, Stanislao Cannizzaro.
Cannizzaro laid out a persuasive case for a new uniform system of atomic weights.
I still remember the powerful impression Cannizzaro made. He seemed to advocate truth itself.
After Karlsruhe, something astonishing starts to happen. Within a few years of the Congress, you start seeing lots of different attempts to organize the elements that are all based on these new post-Karlsruhe weights.
A French geologist arranged the known elements in a spiral along the outside of a cylinder, like the stripes on a barber pole, and found that elements with similar properties tended to fall into columns. An English chemist arranged the elements by atomic weight in rows of 7, and found that their properties repeated like musical notes 1 octave apart. By the end of the 1860s, 5 different European scientists had detected glimmers of a hidden order among the elements, but no one could quite put the puzzle together. That's where things stood when Mendeleev finally landed a professorship at the University of St. Petersburg. One of the duties of his new post was to teach introductory chemistry.
He has to teach this class, hundreds of students, and he has to give them a textbook. There are no up-to-date Russian language college-level textbooks available.
So Mendeleev set out to write his own, Principles of Chemistry, in 2 volumes. He completed the first volume in 1868, and on Friday, February 14, 1869, he sent the first 2 chapters of Volume 2 off to his publisher.
Marina.
He was in a hurry to finish it because he was struggling to make ends meet.
То же самое место, номер 36.
He hasn't yet gotten any royalties from the textbook because it hasn't been written yet. He's got to keep his family fed and clothed. He has, at this point, 2 children and a wife, so he was always looking for more funds.
To make a little extra money, Mendeleev planned to take a short break on Monday to do some consulting for a cheesemakers cooperative. But he had something on his mind. His publisher was expecting the next chapter of his textbook in 2 weeks, and he still hadn't settled on a way to organize the rest of his book. Mendeleev had spent most of the first volume covering a few common elements like hydrogen and oxygen in great detail.
You learn a huge amount of chemistry, but it's slow. Volume 1 contains just 8 elements out of the 63 that were then known.
When it came to writing the second volume of his textbook, Mendeleev realized that he had better find an organizing principle fairly quickly because he had to cover the remaining 55 elements.
Since I'd set out to write a book called Principles of Chemistry, I felt I had to establish a system for classifying the elements. A system based not on chance or guesswork, but on some sort of principle.
Изволите чай?
The problem gnawed at him all weekend.
He's trying to come up with a way of packing more elements in the same amount of space. He couldn't ramble the way he did in Volume 1, however useful that was.
Mendeleev had already hit on the idea of focusing on whole families of elements rather than treating one at a time. Chemists had long known that certain elements resemble each other in much the way family members do.
You can often tell people are related because they have the same sort of face.
They have the same nose, they have the same color eyes. There's something in common, and that's something very similar in these chemical families. They tend to react similarly to the same kinds of substances.
Mendeleev had ended Volume 1 with 2 chapters on a well-known family, the halogens: chlorine, fluorine, bromine, and iodine. He began Volume 2 in the same way, with chapters on sodium, potassium, and lithium, a family called the alkali metals.
He realized that a family of elements is a good way of organizing so you can do more with less space.
The problem was there was no obvious family to turn to next. For insight into what other elements might be grouped together, Mendeleev looked more closely at the 2 families he already had.
And in that process, he figures out something rather extraordinary about the elements. He looks at the atomic weights of sodium and lithium and looks at the difference between them. And then he does the same thing for fluorine to chlorine and notices that those 2 differences are very close to each other.
Was this just a coincidence or a clue? Excited, Mendeleev wrote down the lightest elements and their atomic weights. After 7 elements, he broke off and started a new row, keeping elements with similar chemical properties in the same column. The numerical pattern continued to hold.
The eye is immediately struck by a pattern, a regular change in the atomic weights of the elements within the horizontal rows and the vertical columns.
He notices that there's a regularity in the differences. That is, the changes that happen within a family happen regularly across families. And that's the fundamental insight that gets him thinking about how to organize all the other elements.
Mendeleev had begun the weekend trying to solve the problem of what to do next in his textbook. But having reached this aha moment, he dropped everything else and he poured all his energy into revealing an absolutely fundamental principle of nature.
When he was taken by an idea, he was really taken by it. He starts putting together this system, and he's trying to figure out the hard spots, the things that don't quite make sense. Maybe I can scratch out this element here and put this element in its place. Should I change the atomic weights? Do I have to rethink their properties? And the problems of it, the intellectual puzzle, just grabs him.
The challenge Mendeleev faced was similar to one of his favorite diversions, the card game called Patience, in which the object is to arrange playing cards by both suit and number.
That process of keeping several different variables in mind is kind of analogous to how Mendeleev was thinking. He started using both the regular increasing order of atomic weights and the relationships of chemical properties with each other to build two dimensions.
Mendeleev didn't just lay out the known elements in order of rising atomic weight.
When it looks like the next element doesn't have the properties it's supposed to have, he scooches it over and leaves a blank spot.
And has the audacity, has the daring to suggest that there might one day exist an element that would fill that space.
The few scraps of paper left from Mendeleev's struggle that weekend reveal that he sometimes arranged the chemical families in rows instead of columns. Unhappy with this early attempt at a table, he moved the alkali metals to a new position in the next draft below, but kept them together.
Mendeleev is not moving elements individually, but he's moving them as a block. It's as if it's a composite piece of a jigsaw puzzle that he's moving all together.
On Monday morning, a driver arrived to take Mendeleev to the train station for his trip to the cheese cooperative. He was well into his task, but still struggling to make all the pieces fit. We know this because one of the surviving fragments is a letter delivered that morning concerning arrangements for his trip to the cheese cooperative.
And on the back of the letter, which still bears the stain of a cup, Mendeleev has sketched a few symbols and has carried out some very simple calculations. He's looking at differences in atomic weights.
So he was still working on the problem, even after wrestling with it all weekend.
Карета ждет вас внизу.
The drafts of Mendeleev's table show plainly the struggle he went through.
At the bottom of the page, he lists the elements to be classified. As he fits them into the table on that page, he crosses out the elements. It's just what you and I would do. We can see the effort in that page. He's making mistakes, he's correcting them. It's full of crossings out. There are things that don't quite fit. This is a human being trying to understand this world.
Hour after hour, Mendeleev worked on the table, missing one train after another. Finally, he dismissed the coachman. The cheesemakers would have to wait.
Кто там?
Александр Алексеев приехал.
Дмитрий Иванович, здравствуйте.
That afternoon, a visitor found him distraught, unable to capture the order he knew was there, just out of reach.
Не могу найти.
Ничего, у вас все получится.
Later that day, Mendeleev came to a choice that would crystallize his thinking. The elements involved were iodine and tellurium.
Iodine's a little lighter than tellurium, so it should come first. But Mendeleev looks at that and says, well, if I put iodine first, it's in the wrong family. It's actually a halogen, which is the next row down.
If he stuck to that weight rule, it would put an element outside of the family it obviously belonged in.
So he decides tellurium, the heavier element, should go first. It always bothered him that iodine was lighter than tellurium but came after. That breaks the order of atomic weights, but it preserves the family resemblances, which are more important than just the increase of atomic weights.
With that principle established, Mendeleev hurried toward the end.
And the more he worked on it, the better it looked.
Finally, that evening, Mendeleev completed his table. Before leaving the next day, he ordered 200 copies printed and sent to leading European chemists.
By the time he left for the cheese factory, Mendeleev knew that he was onto something extremely important. I think he realized that day that he had cracked it.
With a few modifications, soon made by Mendeleev himself, his 1869 draft is easily recognized as the periodic table of the elements, incomplete but unmistakable. In his published table, Mendeleev left blanks for some of the elements he thought were missing.
Not only did he leave a blank space, but he suggested an approximate atomic weight for that future element.
And the fact that Mendeleev on that first weekend is already thinking this way, that's a sign that he believed that there's something deeper going on here.
Mendeleev believed his table was more than a convenient way to arrange the elements. He was convinced he had discovered a law of nature, that the properties of the elements are determined by their atomic weights and vary in a regular, periodic way across the table.
It's periodic because the properties of the elements repeat in a regular fashion. When you wrap around from one row to the next and come back to where you were, the elements that are in the same column have similar properties.
He had an almost mystical feeling that this was there in nature and not so much a human invention as a discovery.
Given the remarkable regularity of his table, Mendeleev couldn't believe nature would have just left some spaces empty.
Laws of nature do not permit exceptions.
There must be an element which we have not yet discovered. Go look for that element.
And he was bold enough to not only to say an element is missing, but to predict.
The periodic law allows us not only to predict what new element will be found, but also to determine in advance their chemical and physical properties.
In 1871, Mendeleev published an article making predictions about 3 of the missing elements based on the properties of their neighbors in the table.
Chemists really weren't used to making predictions of any kind, let alone ones to this degree of specificity. They are remarkably precise and quite daring for Mendeleev to print them.
4 years later, a French chemist found a new metal so soft it melted in his hand. He called it gallium. It seemed to be a good fit for the empty spot below aluminum, but the density didn't match Mendeleev's prediction. He wrote the Frenchman suggesting that he check his data.
So you can just imagine this Frenchman who actually has the element in his hands, hearing from this Siberian who has never seen the element, and daring to say to him that he's made a mistake.
But sure enough, when the French scientist rechecked his measurements, Mendeleev was correct.
So not only had Mendeleev predicted the element, but he knew the properties of the element better than the discoverer of the element knew them.
Within 15 years, all 3 of the detailed predictions are discovered, and that catapults Mendeleev to chemical superstardom.
I never thought I would live to see my ideas verified. I was wrong.
But in 1894, 2 British scientists made a discovery that threatened to bring Mendeleev's carefully crafted edifice crashing down. They found a new gas they called argon that didn't seem to fit into the table.
When Lord Rayleigh and William Ramsay discovered argon, it looked like a problem, a very serious challenge to the periodic table itself.
Mendeleev's first reaction to almost anything that was contradictory to the system was to be hostile to it and suspicious. And Mendeleev therefore decides it's not an element. There are lots of reasons to think that. First, it doesn't react with anything.
Chemists couldn't get it to do anything. It was inert. It behaved like no other gas that anybody had ever encountered.
And secondly, it has no place on the table, so how can it exist?
Matters got worse when Ramsay announced he'd also isolated helium, 30 years after it was first detected in the sun. It was definitely an element, and it too had no place in the table.
And then just 3 years after that, William Ramsay's research group discovered 3 new rare gases, krypton, xenon, and neon.
They display the same kind of properties, they're all inert gases, and they display the same increase of atomic weights as the other natural families do.
And that changed the situation dramatically. What began as a single anomaly, a single puzzle, now looked like a group of elements
Now we can see that helium, neon, argon, krypton, and xenon are as closely united as any other group.
And so Mendeleev makes the single biggest revision to the system he ever did. He puts in a new column, and that is the family of noble gases.
My periodic system is in no way injured by these discoveries. In fact, they confirm and strengthen it.
It turned out to be a vindication of the periodic system, and if anything, made it even more profound, the discovery.
Mendeleev's table had finally brought order to chemistry's unruly garden.
After Mendeleev, one could see that each element had a place. It was a grand design that worked.
Chemistry wasn't just one thing after another, random substances we've dug up from the earth. They are interlinked in a complicated and rich way.
We are at the dawn of a new era in chemical science, approaching a new understanding of the still mysterious nature of the elements.